Mohammad Shojafar, the second author of the paper entitled by a novel distributed fog-based networked architecture to preserve energy in fog data centers, one of the new emerging paradigm in cloud and emerging technology in the distributed systems. So we're going to plan this work in here by starting for the next slide. So as an introduction, I just want to highlight the concept of the fog computing. So fog computing is a new computing paradigm that extends cloud computing and services to the edge of the communication networks. On the other hand, we can target the concept of the fog computing, which is involved of various type of applications that can run both in the cloud and in devices. Especially for the billion of devices, it could emerge interconnecting of the various concept of Internet of Things, of different devices that could connect to the Internet by using this technology. So, you know that the Internet of Things, it's a very generalized system that could able to handle data and energy in complex systems. In a way that they could cover the electrical grid of the network and other complex networks. On the other hand, fog computing comprise of various fog nodes, which are devices inside of the fog computing as a nodes or as an internal component that could communicate and make a chain of the fog nodes to make a fog computing abstract. So the fog nodes are the architecture that provide resources for services at the edge of the network. And they could consider as this kind of paradigm that these devices could call a group of these devices, a network of the fog nodes, that we called it a fog computing platform, which is defined clearly and neatly in the paper. And by considering this pre-information of the introduction, we could consider in our paper, so in order we plan to concentrate on the fog computing, specifically on the fog nodes of the fog computing paradigm, and we plan to present a fog data center as a joint managing of the fog and IoT paradigm with a target of reducing energy consumption and the operating cost of fog-based systems. In order to cover this case, we present and introduce a novel architecture to perform real-time IoT communication over fog data centers. And moreover, we detail the fog data center in the next slides over a IoT-based environment and the features. Moreover, we go toward for the mathematical aspect of the fog data center and present a mathematical problem with the target of the minimization of the total energy consumption of the system. And after that we will present a heuristic algorithm to preserve a load balancing and resource management over fog data center by considering of the IoT aspect of the system. And we evaluate the proposed algorithm through extensive simulation based on a real world data that we gathered from the case studies. So let's start by defining our generalized architecture. So as you see in this slide number 5, it is presented the IoT architecture and fog computing, which is a combine of distributed edge located processing and control applications. You can see different set of the network are emerging in these slides, and they are connecting with a real-time secure connectivity framework, which is called fog computing. So you can see different fog nodes. There are different nodes of the system. They reside a fog computing, and inside of the architecture you can see a machine-to-machine communication infrastructure and the machine to the control center. The control center, which you can see here by showing my cursor over it, which is Fog Data Center, acronym by FDC, which is a machine to cloud data connectivity connections. So by considering this aspect, we go toward to definition of different parameters inside the systems. So you can see in the FDC is dedicated to supervising a transmission, distribution and communication network. So you can see all these concepts are required to precisely manage grid architecture, the data and the energy coming from the wind farms, coming from the smart homes, and coming from the other components such as the electrical vehicles, which is stand for EV, and solar panels and some other resource of energy. So they are receiving these informations, which could be the electrical information and some other information. We just want to interpret that information coming to the F data centers, to the fog data centers. And so these lines that you can see is a bidirectional lines that they could transfer the data communications, so the communication from the distributed generations, interactions of the different sensors, and the power electrics. Besides, the Internet of Everything application, or the huge amount of the data is coming from this kind of architectures, that they target different devices and different application they want to use this kind of information. So we have to propose a new techniques in order to how can distribute this kind of loads that come into the system, and how we could balance this information due to the hard limit time for each data, for each service requester, or for each devices or the machines that they requested this information. So in order to go toward to the model, we would like to highlight the various components, the sensors you can see when I explain that they have capability to cover Internet of the energy, and the fog node based energy coverage that they could help the customers to maximize the cost of resource efficiency and minimize the energy of the environments, and they could control the performance and using the fog advantage to apply locally and remotely on the real-time data processing. If we focus on fog nodes and fog devices, so we use interchangeability sometimes in my discussion, fog nodes and fog devices based on each other. So most of these concepts are the same as each other. And so the fog networking and inter-fog communication, that could be simplified as switch routers, embedded servers that are naturally near to the things and generate and process Internet of Everything data that coming to the system. So the function of the fog nodes is to manage information and energy and perform customization and meet the needs of the system operations. Moreover, the fog node is able to analyze time-sensitive data nearby the things and producing data. So let's go discuss about energy storage devices. So you can see the energy storage devices, which are coming from the devices we explained about the storage of the device, storage of the energy that is coming from the producer of the energies, which is called EST, is a significant part of the Internet of Energy. And they could improve the quality of the power and the quality of the generator, because they could add energy in the systems. Not only they consume energy, but also they produce energy to the system in order to facilitate the processing of the request and increase the energy of the system, energize the systems. So we would like to care about this concept in our model, which is addressed clearly from the smart grid point of view. Let's talk about let's call it the details of the fog data centers and the architecture of fog data centers. So you can see in the architecture of the fog data centers, each processing unit executes the currently assigned task, but self-managing local virtualized storage and computing. On the other hand, you can see that if in this figure, which is talking about the IoT architecture on fog computing, slide number 9, we would like to explain about the blocks. So the first block is a access control server, which is, you can see the cursor over it, and the router, which is task is to dispatch the incoming traffic or incoming data and coming to the system, to the data center. The second component is reconfiguration computing system, which is talking about a cloud management of the virtual machine monitors and load balancing, which call it dynamic load balancer. The third component is talking about switch virtual switches that is coming from the LANs. So in the fog data centers, we have different servers. Each server is residing on different virtual machine could run it. So we have a maximum length of the virtual machine could run on each physical server. And each virtual machine could respected to each application, each data of the application coming to the systems. And you would like to care about the switching of data from a dynamic load balancer to the each physical server and vice versa. So this is a communication bandwidth, a connection they call it TCP/IP connection bandwidth. This is a parallel TCP/IP connection, and they connect to the bank of virtual machines that this virtual machine residing over a middleware virtual layer and over a physical switch network. So in this problem, which is the problem is going to be detailed on the fog data center as we explained before, we're going to minimize the total energy consumption from the computation part, which is the computation for each virtual machines, from the communication from virtual machine to virtual switch and dynamic load balancer and vice versa, plus the interchanging of the virtual machine frequencies. So if we go toward to this system, we have a time slot for each request because we would like to respect the real-time case. So we have a duration which called the time slot. The time slot, which is stand for T total, the T is a discrete time slot index and spans a semi-open time interval between this interval that they could be responded a request based on these tasks. So we have a set of the physical servers, we called it S, and a set of the virtual machines, we called it VM, in order to respond to requests. And also the incoming workload that is coming as an input workload to the system as it comes to the input queue. It called it L total, which is a total workload in this time slot that coming to the system. It could be dispatched in each virtual machines and each servers. So the Li is the amount of the workload that it could dispatch on each virtual machine on each server. So by considering this concept of general concepts, we go toward to the modeling of the systems. So the modeling could be considered in two parts, as I explained. The modeling of the fog data center computing energy consumption and modeling of fog data center communication energy consumption. The computation, which is shown in the first formula here, you can see, it's comprised of the energy idle plus a quadratic function of the maximum energy consumption of each CPU and minus the idle energy consumption, which is a quadratic formula is coming from difference 12, which we proposed before. And just I want to highlight that FSV is the optimum processing rate of each virtual machine V on server S, and FSV max is the maximum processing rate of each virtual machine on virtual machine V on server S. I just want to again highlight that E idle is an inactive state of the server, and the maximum energy consumption of the server S called E max. So the second model is talking about a communication model, which is, I just want to highlight to you, is a communication from virtual switch to the virtual machine, this line. So which is a linear one and which is a wired one. So it could comprise of using a TCP New Reno protocol, the Cisco model, which is our let's call it our partner that you're working with them. And the model could be simplified as in here, and so it's a transport layer connection from the energy between a virtual machines and the virtual machine switch, and we would like to address this energy plus this energy, which is the third formula in here, to minimize the total energy consumption of the system. So in the next slide, you will see the minimization of the problem subject to some of the equality and non-inequalities. The first equality, which is talking about is going to guarantee the overall input workload coming to this to the input buffer or input queue, which is L total I explained before, from the offered fog data center at slotted T is partitioned over the available virtual machine in the feasible manner. The equation number 2, the inequality number 2, which is you can see in a cursor, which is talking about controlling the maximum workload that each virtual machine could be served should be less than the maximum capability of that virtual machine. The next equation, which is talking about limit the processing rate of each virtual machine, that it could control the frequency of that virtual machine should be less than the maximum ability of working frequency of that virtual machines. And it could be clear from the last formula even that it could emphasize that this model, the second figure talking about FTC, should not be more than the maximum frequency that it could be responded in each virtual machine. So the model could be an optimal model. In order to speed up the system and try to use it in different fog nodes, various fog nodes in a scalable manner, we propose a greedy solution, which is a simple algorithm to solve the problem. So we consider problem as a bin packing penalty aware problem. So for each incoming workload, we calculate the number of the virtual machine could be allocated to for each time slot to the system, and we consider server as a bins and virtual machine as a packs that must be served distributedly in the time limitation and the frequency limitations. This process continues in some iteration, and after the iteration we give penalty to the system, to the server. I mean, the penalties is done on servers based on their energy characteristics, from the energy, idle energy, and the maximum energy and the maximum frequency of the server. And the penalty and the revolt policy could be considered in order to decrease the fatality cases, such as the exponentially increasing the energy consumption and so on. And the penalty means that the server could be punished and banned to be used again for some iterations. So in some iterations it could be freezed. So when the freezing iteration for the server passed, so the server could back to the list of the available server to remaining iterations. So in order to go through to this situation, I just want to highlight that finally, in each iteration, we are looking for the best servers to be allocated. So this process is done in each time slot until the incoming workload will be served. Finally, we calculate the energy consumption component of the optimization problem for each slot. So this is a great solution that we try to explain in the paper clearly with using the definitions. In order to validate this problem, we would like to compare this problem with two existing solutions. So let's go to discuss about the simulation setup of our outcome. So in this test, so the fog devices are assumed to be placed in the intranet and it's bounded by geographical area. Moreover, each device closer to each fog node should have rapid access to the services deployed on fog devices. So I just want to highlight that the fog node and foglet, which is the instance of the fog node in iFogSim, is a software that we use for the simulation, is completely the same as each other. Moreover, that we could see that the fog devices could store data temporarily for the processing. So also, as you can see from the table 1, we illustrate the configuration of different type of fog devices in our model. So we require low latency communication between fog DCs, so different devices you can see in this plot. And the set of the fog node control strategies, and fog node could handle a large amount of data and an intensive computational analysis without burdening the network into the state of the congestion. So we try to use a DVFS techniques for our CPU or each fog node, which is coming from the Intel, and using Ubuntu in order to simulate this kind of situations. We use the IFOC sim, as I explained before, for different configuration of the model for the fog node and the topologies. And the paradigm and the setting of that kind of IFOC sim is completely inspired by a reference 13 and 3, which is a very famous definitions. And also we assume that each fog node support smart metering devices, that it could deploy the energy supplies to from the each home level that it could receive the information. So you can see the CPU range, the RAM, and the latency of each devices in here. And the figure number 2 explain about a range of the frequency DVFS technologies for each fog DC's server, and the range of the idle and the Fmax frequencies. So you can see the maximum is 200 and 400 joule of the energy consumptions of the idle and the max idle for each server. So in order to compare this situation, let's go to the comparison. The first comparison is talking about the performance comparisons. The first slide is tested energy performance of the proposed heuristics of the greedy solutions in various communication ranges. So you can see that we use in this plot we define 10 fog nodes, and each fog node have more than 5 virtual machines instances on run it. So we use a WordCap 98 traces the real input traffic coming to the systems, which is coming from reference 16. We define fast, giga, and tera Ethernet. So the fast is 1.8 10⁻³ gigahertz, and the giga it could be 2.5 10⁻², and the tera is 1.1 10⁻². So you can see that it should highlight that the average total energy consumption, which is stand for E total bar based on the joule, for the various range of the communication is different for in each fog node, in each fog nodes that you can see in the system. Also, we compare the results with our solution, which is called greedy solution, with two very famous approach, MBFT and MDC. MBFT is coming from the Professor Booya lab, from the cloud lab of the Melbourne University, which stands for the reference 14, and MDC, which is the other solutions, which is stand for maximum density consolidation approach with 4 cases. So for the 4 test case scenarios. So that we try to use this kind of testing to compare the reduction in the overall average energy consumption of the various network shapes. So we will see that in the total energy consumption, instantaneous total energy consumption of the situation, we have a different number of virtual machines. And so this first set of the figures, which is in the upper part of this slide number 16, is going to highlight that we're going to report the instantaneous energy consumption and saving of the greedy solution to the submitted real workload for various shape of the arrival process in the system. And you will see that for the figure for the average comparison, here you can see the comparison of this result for the average energy comparison of this result for these 4 scenarios. You will see that 81.55 and around 64%, our approach is much better than MDC and MBFT as a two state-of-the-art solution for comparisons. And the same policy you can see for the energy saving in the second set of the comparison of the same scenarios. And you will see that around 34% our approach is much better than MDC, and around 50% is much better than MBFT for saving the energies. So, and the last plot is talking about the comparison of the different solutions for the various energy consumption, total energy consumption for turn on virtual machines. So we can see if we use more turn on virtual machines, the number of the virtual machines is increasing. The systems try to find the solution much faster and try to distribute this case in much easier way. So you can see the total energy consumption of this plot shows that it decreased and increasing the virtual machine could affect on the results, and the minimum value doesn't vary with changing of the virtual machines. And so you can see two uppermost plots. Uh, as you can see, the optimal value need to driving to the minimum decrease of the systems. So it could strictly our approach compared to the two other solutions reduce energy much higher than their solutions, because we try to use it. Our grid is much faster than the other greedy solution that they propose in order to cover the general case of the problem. So to be conclude our solution, we propose a distributed Fox supported network that we focus on the smart grid application which are described before, and also we explore the FIC platform and the characteristics and using them as a IoT based architectures. We focus on a different performance evaluation of the real world traffic I explained, and validate our proposal in total energy and various cases for fast Ethernet, Giga Ethernet, and and Giga Ethernet with two MBFT and MVC solutions. And our outcome is, you can see, is using several modeling techniques, and it try to care about the SLA and quality of service of the FTC. And this FCC case study use a mathematical model for the systems, and we care about computation and communication of the system. And we try to solve the problem using a greedy techniques. And also for the future case, which is working by a Cisco, our team, and some other European project that our team are engaging with, we plan to care about the security of this problem, which how we could care about the fault and the secure and the problem case for the each fog node, how we could find a routing between, how we could control the information between the fog nodes, and how it could affect on each other if we found a malicious or we found an intruder system in this problem. Now we are targeting this case by the help of the Cisco, and we are working on this outcome, on this work for the outcome results. Thank you very much for the time, and hope this presentation would be useful for you. And I'm glad to take a look our next works that we are working on in our projects, in our Sprites project, and also we can care about other CNIT company that we are working on for an emerging paradigm of the Fox system in a practical case that we are working on. So thank you very much for the time, and hope to have other discussion in the future. Thank you very much.